then I just want to remember here where we left off. We were talking about confidence intervals for the slope. And so we say they all have the form of, you're wanting to estimate a slope in the population. We have a sample. So you have your sample slope. We're calling it B1. And then we say plus or minus some critical value of either T or Z, because that we said that the sampling distribution of the slope followed either a T or a Z curve, and T is what we use when we have a smaller sample. So this example had a sample of 25, and we said there were 23 degrees of freedom. And so we looked at the particular T curve with those degrees of freedom and found the critical value corresponding to 95%. What does that mean? That means, you forgot, that just means that you have this T curve, right? It's something like that. And we have 90, there's one for every different sample size, 25 every different degrees of freedom. We have 25 in our sample, minus 2, 23 degrees of freedom. And so this 95% corresponds to this middle area here. And then this right here, which turned out to be 2.07, so between negative 2.07 and positive 2.07. If you sampled from the actual population, with the true population, this is 0 as a T, and the true population slope right here, 95% of the time you'd be within these limits. So when you, within 2.07 in either direction, standard errors, that's what it means, standard errors. That's how many standard errors you're going to, 95% of the time. That's just that's just a PDF, probability density function of this curve. So when we get a sample, a particular sample, we don't know all this, whereas when we get a particular sample, 95% of the time we think will be in this interval. So that's what this is about. All right. So our sample slope, in this case, was negative, a slightly negative sample slope we got. We're wondering if the number of drinks you have predicts your GPA. And so we're trying to predict this on the whole population. And in our sample up here, that's what we got, that at the top out of 25. And this is like, okay, let's say we did this randomly sample from all 28,000 undergrads here, and we get this. So the question is this, and we change that to a slope, right? We got that as a slope. That's not here, but you know how to do that. What would you do to change this to a slope? You would say, you're just getting the sample slope, and you'd say what? The sample slope is equal to R times the ratio of, R is in, we're trying to predict GPA from drinks. So it would be in standard deviation of the GPA over 5. And that's where we got that from. And that's in units what? What is that? That's GPA points divided by drinks. So if you want to make it interpret that, it's just what that's saying is that on the average, for every drink that students consume, their GPA consume per week, their GPA on the average goes down by 0.02 points. That's what that means. Okay? So whether that's important to you or not is one question. Like you might think that's tiny, and it could still be statistically significant, or vice versa. But those are two separate questions. All right, so we've got that. And so now we want to say, now the question we're asking is, how confident are we that if we actually polled every single person in the, this could just, this negative correlation could just be due to sampling error, right? So we want to know how confident we are if we polled everyone, maybe that the negative would hold up, or just, we want to put some error bars on that. That's all we want to do. Yeah, that's our best estimate right there. But And this standard error, that's our best estimate right there, okay? And so what are we doing here? We're just saying, okay, we want to put some error bars around it. What's this? This is just a measure of the standard error, the typical error every time you sample 25, every time you see it has the N in it, every time you sample 25 tickets, you're going to vary about by that much. But then what's this? This is like, well, how many now we want to put some, how confident we are. So this is just a standard error, but now the more interesting question, probably the one you want to know is, well, how sure are we that it's going to be within a certain margin of error? So we say this is the number of standard errors, give or take this many of standard errors, we can be 95% sure, because these two things correspond on this curve. This is for the t. If we were using the t, if we were using a z, we'd have a narrower one. We'd have a narrower, we would be more sure. We have a wider margin of error here compared to the z. Why don't we say that? That's the question. How does it compare to the one obtained by the z? Well, how does it? So if we were doing the z, what would we do? It's the same exact thing. It's just we'd have to change this, right? Because now we'd be doing a z star. And now we have a choice. We could either do the standard, we could still do the standard error plus of the slope, but typically people don't make that little adjustment, okay? But this adjustment is not going to matter that much. I mean, you could do that. If you're using the z, it doesn't really, this is the part that's really going to change here. And we're looking on a different distribution, and let's see how they compare, okay? So if you want to be 95% confident using the z, you probably know that it's going to be negative 0.02 plus or minus, if we want to be pretty accurate, 1.96. This is narrower. This is narrower times the standard error for the slope. And this also is going to be a little smaller, right? If we wanted to, but that doesn't depend on the z. That's just, this is going to be the bigger effect here. And let's see how, this might not look so big to you, but it really depends on your sample size here. So let's see what we would put in for 95% if we had a really small sample. So let's just look at the t-curve so we can understand it a little better. So let's just go back here and look at that. T. Here's the normal. Now here's the t on page 156 in your books. And so we were looking at this line with 23 down here. And how did we choose 2.07? Well, sorry, this t-table, it just depends on the table you have. This happened to give us a one tail, right? And so remember, our confidence, if we're looking at a confidence interval, a critical value, on this, we want to say 95, we'd have 2.5 on one tail, 2.5 in the other, and 95% would be in the middle. All right, so for a 95% confidence interval, we're looking at this column. Now look what happens. What if we had just, what would a degree of freedom of 1 mean? What would your sample size be, 1 point? Degree of freedom, n minus 2. So what would your sample size be? 3. You can't have smaller than 3. Your degrees of freedom are n minus 2. Think about it. You can't even have a line if you have 1 point. With 2 points, would your slope ever, with 2 points, you have no error around the slope. You'd have 0 error to estimating thing. It would just be a straight line. 2 points determine a line. So you need at least 3, a sample size of 3. Okay? So now with 1 degree of freedom, look at this giant critical value. That means that think what it would mean. It would mean you'd have to, like, that's a very big, That would make a big difference. That's a huge margin of error. Plus, your standard error itself would be bigger. So basically, with 3 points, you have a lot of error, a lot of uncertainty. Does that make sense? Okay. I mean, think about it. The wider your confidence interval, if you want to be 100% confidence, we can just say it goes from negative infinity to infinity. It would do giant y, you know. Wider your, if you really have total uncertainty, your confidence interval is very wide. All right, so that's one thing. And what else do we need to look at here? Maybe while we're at this picture and explaining this, well, let's move on. Let's get to where we're going to go. Maybe we can come back to what I was going to say. All right, so now let's see where we are. That was where we ended up, and where are we going? Okay, that's where we were. And let's just look at this summary here, because I don't think it's clear. So let's just remember our assumptions. We had those 4 assumptions. Now, linearity is basically number 1 assumption, but basically it's included in independent errors. So often, before I begin, you're going to see everywhere this term, IID, you know, your errors, I'm sure you've seen it already, distributed as IID, normal, 0, sigma squared. And this just has that they're independent, assumption number 2, and this is they're identically distributed or equally distributed. So this right here means they have, let me just show you these. This is equally distributed. That's our assumption number 3. And it means that the spread is the same across all the x variables. The spread of the y's is the same across all the x variables. Equal variability. And then we have this one, independence. And that's number 2 assumption. And actually, if independence is violated, then certainly linearity is violated. So it's sort of a sub-question under this, which is why it's often not included, because this linearity, if they're not linear, they're never going to be independent. So, but it's just nice to, everybody says linearity to begin with, even though it's, when you get into higher level classes, they don't mention it because it's included under independence. So that's why I didn't include it here. Okay, so equally distributed independent errors. Now, and that's for large samples, you're fine. You compute the standard error, and then we build confidence intervals using the z-curve, like I just showed you, right? Or the t-curve or the z-curve, right? The z-curve here, sorry. Now, here, for small sample sizes, now this is where we need all of those assumptions. This is where the normality comes in, only if you're doing this. So this is equally distributed, and I should have put in, I didn't put it in, equally and normally distributed. So this is where you need assumptions for too. This right here is the number 4 assumption. So this is when you, to use the t distribution, not to do this, to do this. All right, so that's the idea with the assumptions. And now you understand about these confidence intervals. And any questions before we go on and look at how the confidence intervals relate to hypothesis testing? What the difference is between the 2 of them? Are we good? All right. So let's move on to chapter 10, which is pretty short. Okay. So we're on page 38, chapter 10. And all right, so sometimes instead of finding confidence intervals, right? Like we've just been doing. We want to get a p-value. Why? For the null hypothesis that the true population slope is 0. We just want to make a decision, and that's called doing a hypothesis test. And you say, if the true population was 0, the null hypothesis, how likely would it be to see a sample as far from 0 as what we got, or more, or further? And that's called the p-value, right? That's what we've done before. And you'd probably see the relationship between the two of them right away. You probably would guess that you would just take the confidence interval around the slope, right, and ask whether it includes, where's our confidence interval that we just did? Is it this one right here? A confidence interval around the slope. So we have, this is assuming, right, if we were using a t-distribution, we're assuming there's an RT, and here would be our, this would be as a t-distribution, this particular one, and this for 23 degrees of freedom. And then right here would be the slope. And what we say is the true value of the slope, you know, this is the true value. And we just have our sample slope here, and it follows this distribution. So we say that, okay, what do I say here? Let's write it. You might guess that if you just took the confidence interval and ask whether it includes 0. What am I saying here? If B is outside, for example, we'd reject the null at the 5% level for two-sided. And okay, so let's just understand that before we go on to make sure that is what you'd be thinking, because that seems completely reasonable. So, so that says what? That if we get a sample that is outside, right? We ask whether it includes, if it's outside. So let's say we didn't this time, by the way, did we? Our sample included 0. Our sample included 0. And remember what that tells us. When our sample included 0, what should we be thinking? We should have thought about this. We should be thinking, hey, we're not 95% confident that the true population slope is negative or not. We don't know. It's included in here. We can't be sure, right? In fact, let's look right here. We skipped this part. Let's highlight it. We should have thought of it. This is back on page 34. Since the interval equals 0, and this would be true, includes 0, we can't be confident that a negative correlation in the population, that there's a negative. In other words, that might be due to sampling error, right? So wouldn't that be the same as saying, hey, we can't reject the null, right? Could just be, nothing's going on here, just could really, the null is always that it's just 0, you know, that anything you see in your sample different than that is just due to the luck of the draw. And so, yeah, we didn't really, you can't reject the null, right? Now, so the idea is, that's what you'd think. And so now we get back to page, here we are. And what are we thinking? So we should be thinking, okay, let's take out our picture again. And what if it was outside? What if it, once you translate it into a t statistic, see, if we build confidence intervals as an actual number and go either direction by this amount, let's say we're outside the range, that's going to happen what? 95% of the time, let's pretend we already standardized it. It's so much easier, okay? So now we're just in the t statistic. So now 95% of the time, when we take whatever we get and go and say minus 2.07 and plus, we will include 0. But if we're 5% of the time, we're going to be outside that range. And we would say, we would reject the possibility, we would reject the null that it's 0. Because 5% of the time when we go 2.07 and out, we're just, like let's say we're right at 2.07. You go down 0.07, 2.07, up, we're right at 0. So anything over here, we're not going to include 0. Same here. If you get the negative, that's where we are, right here. So you either go that direction or that direction. That's the dividing line. So if we're on this side of it, then we are going to we're going to be wrong. Our estimate that this is the, or this whatever we sample slope is that we think that captures the population, the true population is going to be wrong. Okay? So that's the same as rejecting the null at what? 5% level. Remember, rejecting the null is, this is p-value. So you can either think of this as a one-tailed test, or either direct or one, it would be 2.5%, or a two-tailed test, and it's 5%. So that's how it matches up. A 95% confidence interval, people always say, is equivalent to a what? A two-tailed test of 5%, or a one-tailed test of 2.5%. All right, so the procedure would be to check the assumptions and then look. And then we would look at this statistic, and you'd say, you can think of this as, if you were doing you could look at, let's pretend we're not doing the null hypothesis, but you'd look at this statistic, your slope over your, you're just standardizing it to a t-stat. It follows the t-distribution, right? Your slope over your standard error for the slope, for that slope, right? And so let's do that. I mean, for a hypothesis test, it would be your observed sample slope minus your expected of 0. So it'd be the same thing. For a hypothesis test, you always say t equals, you'd say your observed sample slope minus your expected under the null over some measure of its standard error of the slope. And we do the same thing with the z. And this, the null always says this is 0, so these are pretty much identical. It boils down to this identical. So let's do it and see what happens. So remember what we said our slope was. It's r over the standard deviation of y over the r times sdy over sds. And remember what this is, which will be given to you. This standard error of the slope will be given to you, not the n minus 2. This one will be given to you right here. It's exactly the same thing down here. This standard error of the slope. Okay? You should know that it changes to n minus 2. All right, so we have this. We can do the same thing. Z equals the observed slope minus the expected, that's always 0 under the null. And so this is what we'd have. All right, and then you simplify it, and look how nice it simplifies. I want everybody to look at this because it kind of makes it really easy to remember. That, do you see how the units cancel out? Because that's what we're doing. We're basically just z into your unit free. So this is what we get. So we get this statistic here, which is really intuitive. Let's think about it. It's r over the square root of 1 minus r squared, right? So you can think of this as a measure of your model, the strength of your model, and this is your error. Remember? Together, if you squared them both, you'd say r squared plus 1 minus r squared equals 1, right? So this is going to be the key in all your analysis of regression analysis. Once we add slopes, we're going to square this. But now you also have to think about this part, which also totally makes sense. And your strength of your signal increases when you have a bigger sample size. The bigger, just if you have, if you still see a signal with a huge sample size, the same R is going to become much more straight, much more significant. It's going to mean you have a much bigger signal if you can, right? Because when you have sample size of 3 or 4, Well, you could easily get a big R. It's just there's so much error. Okay, so this is going to be important. What do I mean important? That was stupid. What I mean is that this right here, and let's do it here, is beautiful because for you guys, because it's easy to remember, and I love formulas that are super easy to remember, because you can see in the mean, this is the strength of the signal here. You can think of it that way. The strength of the model or the signal. And this is a measure of the strength of the noise. And same exactly for this and this. It's the same thing. It's just a tweaked version of it, slightly tweaked. And this statistic, when you square the whole thing, will feature in all of our analysis of variance as basically this one will be the chi-square one, and this will be slightly more tweaked, will be something called the F statistic. So it's nice to just see it now and understand. And it's particularly nice because when we actually look at our logic of how we do a significance test, we're really not doing this. It's this that's distributed as a t, and this is distributed as a z. It's not this part, because once you assume, in our significance test, we are going to be assuming that r is equal to 0, right? So this standard error would get rid of that r. It wouldn't have that there. And that doesn't even make sense, because r, it just is, well, it's wrong, but it also doesn't even make sense, because r has limits between 1 and -1, and our normal curve goes on forever. So I'm just saying you can remember it this way, but here we end up with these test statistics that, first of all, are beautiful here because they're easy to remember, and they only involve r, but they don't, even though they look like they follow our usual observed minus expected over standard error, which a lot of the mean follows, they don't. Yeah? And now we would do the same thing here, and now so I was just talking about how it's going to be, let's go to the next page and you'll see what I mean. All right, so it's going to be this is what I'm talking about. And if you didn't follow that, don't worry. This is what you're going to be using. It looks exactly like what you always do. You're always going to be doing this, what you always used to do, but what can I say? Test statistics don't have to follow that form. All we're looking for is some test statistic that we can that we know that has a known distribution that's related to what we're interested in. And they don't always follow this form. This one happens to follow the form. It looks like it, but it's actually this whole thing that's distributed. It's not when we assume that r is equal to 0, like we are going to right here. Around that, the distribution around 0, when r is equal to 0, is not following the t. It's that whole statistic that is. And if you didn't follow a word I just said, don't worry about it. Okay? That's not going to be on, it's way more advanced than what would ever, I don't even know why I'm saying it. It's just like I don't want to say something wrong in here. And for those of you who might be interested. But otherwise, don't even think about it. Okay, so we're interested in finding out whether or not there's a negative slope in the regression equation for predicting drinking from GPA among all UI undergrads. But we don't have the time and money to sample all of them. So instead, we take a random sample of 25. All right, now we're going to do this. Instead of building a confidence interval, we're going to do this hypothesis test. So we find that the slope was equal to what among the 25? We just did it, wasn't it? It was this. I'll just do it again in case you want to see. That one, wasn't it negative 0.2 times the ratio of these two things? Points per drink. All right, so that's what our slope is. we put it right in here, negative 0.02. Maybe the units here make it look how, points per drink. And then the drink cancels out, and we've got GPA. And then we just have to solve here for our intercept. And the way we do that, of course, is by plugging in the point of averages right there for what? For GPA, it's 3. And for drinks, it's what? 10. So what do we have? 10 times negative point, isn't that negative 0.2? We'll just move the decimal place over. So we have 3 equals negative 0.2 plus what? 3.2? Is that right? Yeah. We have 3 equals negative 0.02 times 10 plus this y-intercept. We'll call it beta naught. And I'm sorry, this is beta naught and this is beta 1. All right, so we've got it. And now we've got that, and now we're going to do our hypothesis test. Suppose there's no correlation. That's equivalent to saying that the slope's equal to 0 in the population. How likely would it be to draw such a big difference just by the luck of the draw of this big a correlation or this big a slope? Equivalent. So you're going to find, you formulate the null hypothesis and an alternative, and the null H naught is always like nothing's going on, that the slope in the population equals 0. So let's just pretend we have a population scatter plot, and this is what our null says, that we have drinks here, and we have GPA here. And what the null is that there's our whole population, so there'll be how many? 28,000? What did I say? Whatever. I don't even really know how many undergraduates there are, but let's say there's 28,000. So, and let's say, so there's like, we could, theoretically, there's this scatter plot that exists with 28,000 points, and we're trying to estimate, and that's the null is, we have to say a particular value. What's it going to look like? Well, 0 down here, I don't know what it would go up to. I mean, how many drinks per week? Is the maximum 100? I don't know. There might be somebody who's constantly drinking. Who knows? And the GPA is 4 the maximum? And it's, it's probably going to be small. They're not going to be as many. It's going to be like more around. We can look at our own. Let's look at our own in a minute. When you answered this question, why don't we just look at our own in a minute, okay? So we can see the shape of it and everything. But let's say we're saying, what is the null? What is the null? It's saying that the slope inside here is what? Completely flat, isn't it? Isn't that what we're saying? It's that this is the beta in the population. Beta, the slope is equal to 0. So that means we're not talking about the intercept here. Let's not worry about it. We've got a completely flat slope, okay, wherever it is. Completely flat. And that beta 1 equals 0. That's our assumption under the null, all right? Then we say, okay, we take, well, what is our alternative? Now, our alternative is what? The beta 1 is not equal to 0. And let's just specify, most people think it's less than 0, okay? Or let's say we thought it was less than 0. One-sided, then it would be, because we think it would be negative. That the more you drink, the worse your GPA. Okay. And that observe this difference. What is this? In slope. It's too large to be explained by chance. If we really take 24 points out here, we're not going to get something so extreme. As a correlation, it's probably easier just as a correlation of negative 0.2. Well, how do we know? We have to plot the sampling distribution. And you'd think you'd plot the sampling distribution of R or of the slope, but instead you're plotting the sampling distribution of the entire statistic. That's all. I mean, you would never know it because you could do it the same exact way, but really what you're doing is you're plotting the thing of the whole statistic. Because why? Because what we're doing is we're assuming this. We are assuming this. So if we did it our usual way and said our observed slope, yeah, that with the numerator would be the same, minus the expected is 0, or observed is negative 0.02. But then the standard error of the slope is computed assuming this is true. And if this was true, and there was a correlation equal to 0 here, then this r would be 0, and this would not be our formula. And once you do that, this is no longer distributed as a t. And this is no longer distributed as a z. So it's kind of fake that people tell you you're doing. You're not doing this. It doesn't, I mean, in the statistic, yes, the math is exactly the same. But you're not assuming that you're sampling, that you're looking at the sampling distribution of either this, of r, like that's like of r under the null, that r is 0, because you'd get a different formula. And if you do it like the way I actually was, you can convince yourself, I think it's going to be one of our problems in R, with those of you in the R course, you can look at the distribution and you can see that that's not going to be right. You can simulate it. Okay, but here's it's still exactly the same statistic we're using. And so here's our logic. We're still doing this. We're still saying that we choose n equals 25 randomly chosen points from here. And we get this slightly negative correlation, and it's translated into slope, and we get that, okay? And we get a sample r equal to negative 0.2, and B1, which is our sample slope, and that's our population slope assumed under the null, and B1, equal to negative 0.02. And that is points, it has units on it, this one doesn't, points per GPA. Okay, so that's where we're at. Now, we're going to use that test statistic, and that's what follows the T or the Z. And let's just remember how, so that's explained here. And so we're going to use one of these, and we want to use one of our standard distributions, normal for big enough n, or t for smaller. And these extend from negative infinity to positive infinity. But r itself only goes from negative 1 to 1. So we need some function of r. This is where this comes in. That goes from negative infinity to infinity if we want to use one of these distributions. And that's how we get this. It's a function of r. It's not the distribution of r divided by the standard error. It's just not. That's the idea. All right. So, and that's why we're doing, and this is very common. I'm emphasizing it because in Stat 100 I didn't really tell you this or didn't write it. I always said, okay, it was always of the form something you observe minus expected over some standard error. And I'm saying, yeah, that's true for the mean, for the sum, for percents, for some things. But for a lot of things, it's not. You're just looking for some test statistic that that does follow some known distribution. It's a function of what you're actually observing. It's not that. Okay? So that's all that's happening, because it will come up a lot that your test statistic isn't of that form. All right, so it's it's the statistic itself. Now, I promise you none of that's going to be on any exam. It's way too advanced. I'm sure it's not even on higher exam, but it's just for your knowledge. All right, so here we are, and now we're going to use this right here. So let's do that. Okay. So which one should we do? We're going to use the distribution to find the p-value. So do you remember how we can do this? We're just going to use one of those. What should we do? Do you want to do the z or the t? I mean, really should do the, do you want to do both of them? Just so you can see the difference? How do we decide? N is less than 30. We have a small n. So we should use the t, but let's do both just to see the difference, okay? for fun. You can laugh at that, but just for fun. All right, so, so if we, just because it's, honestly, because I drew the normal curve here, and it's easier. There's just one normal curve, so we can just do this one easily. So let's just do this one. We'll see how far off, how different they are. So how are you going to remember this? Well, we have it right there. So it's R. We don't even have to do the standard deviations. It's so much easier. R is 0, negative 0.2. Okay? Then you have the square root of 1 minus that squared. I'll just say, let's just square it in our heads. That's that. Okay. Times what? Times what? Square root of 25, which is 5. Okay? And I did this, and I got negative 1.02. So how are we going to compute a p-value from that? Well, first of all, this is the z, so we have a 0 here, right? And this is negative, there's 1. We're just going to be a tiny, 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 tiny bit there. Negative 1.02 and positive 1.02. So pretty much in our heads, we know 68% is in the middle, don't we? Between negative 1 and 1 on the normal curve. Everyone should know about 68%, right? Let's estimate. Can we do it? So this is going to be about what? 32 for the 2, and this is our p-value because it's this is what we got. This is our z statistic. I should label this. This is z. And we got right here. Okay? Because I just did that. We know it's about 16%. All right, we'll look it up more exactly in a moment. But so p is approximately 16%. So what are we going to do? Are we going to reject the null? Remember, what the null says is that, that it's assuming that if it's really 0 as a correlation coefficient, as a slope, if it's really here, right, if that's the true population, then 16% of the time, just by the luck of the draw, and 32% of the time, just by the luck of the draw, you're going to be outside those limits. So is that strong enough evidence? That's going to happen to us 16. No. So we usually set, if we are setting the conventional definition, and we can just leave it at that, and that's fine. But usually people say if p is less than 5%, the result is called statistically significant. We reject the null, that it's just nothing's going on, and we say, hey, there's a negative correlation. Don't drink. Your GPA will go, shoo, or slightly down, not shh. It'll just go slightly. You might not care about it. Maybe you'll calculate about how many drinks you have. Okay, so this would be it, and we would reject the null. And I just said it wrong on purpose because I want you to stop me. Would we really reject the null? No. What are we going to do? We don't say accept the null because we assumed it. So we can say what? Can't reject the null? Why don't we just, instead of just saying that, let's say what we mean too. Can't reject a null. Could easily, the difference we see from 0 could easily be due to chance, right? That's what we mean. The difference we see from 0, the negative correlation, could easily be due to chance. I'm saying negative here. I really mean the difference. That's what I'd be interested in. But it's like, the difference we see could easily be due to chance. Okay, and it's really a 0 correlation. Yeah, go ahead. Where am I getting 16%? I'm waiting. Good question. I estimated it. Let's figure it. We can figure it out exactly in a minute. But you know what I did? If I want, where I got it from was that here. It's about 68%, a little bit more. So it's going to be a little bit less. let's go to our calculator because we're going to have to do that anyway for the t, and we'll fill that in and you'll get it, okay? So now we're going on to the next one. That's our z. This is really, I just want to show you how they differ. And they're not going to be so different because we have a fairly large sample size. All right? So now the t is going to give us what? So we're going to do the same thing, just r over the square root of 1 minus r squared. So that's that part. This part is going to be identical. What's the only difference is right here. Instead of multiplying by 25, we don't really have as big a sample because we're estimating, we have to subtract off those 2 degrees of freedom is what we're saying. So we're going to have, so this is, that's one tweak we do. So we're not going to get as, we're going to get a smaller. T is small, t tinier, whatever you want to call it here, stat, t. And it will be smaller in terms of absolute value is what I mean, closer to 0. So that's going to be that. All right, so that's one slight, so it's going to be closer to the center. But the other thing is, I wish I could draw it on top of here, it's going to have slightly fatter tails. Slightly fatter tails, which means we're going to have slightly bigger p-value here. So let's just do it. Now, where did I get that? So the degrees of freedom is n minus 2, which is 25 minus 2. That's where I got that 23. And it's important because now we have to look on the t curve with 23 degrees of freedom. Remember, there's lots of different t curves. All right, so we're going to look at the t curve with 23 degrees of freedom and look up this statistic. We want to know, this is on our t with 23, and 0 is in the middle. And we have, it's about 1. It's not that different. It's about 1, but it's negative 0.98 and 0.98. But even if they were both exactly the same, t is fatter in the tails. So let's say these things were exactly the same. T is fatter in the tails. And so, in fact, this was 1, and this was 1. We can see what it would be. We can look that up. But so we would. This is going to be bigger, but not that much bigger. And if we looked in the back of the book, it's not going to really help us that much, will it? Because it's not so detailed. We'd go to 23 degrees of freedom, and we'd go to 1, 0.98. And all we see is that it's going to be somewhere between 25 and 10. 25 and 10. We can be sure it's going to be a little bit bigger than that, but we don't really know what. So let's go to our calculator. I don't know if you've used this, but let's go here to our PC. And here's our calculator. So we might as well get both of them. We can do the normal distribution. So our value for the normal distribution was negative 1.02, and we wanted the left-hand tail. So let's see what it gives us, and we want to compute the p-value. So it's 15.39. You can write that in your books. I'm going to write it before I forget. We said approximately 16, but it's 15.39 to be exact. So maybe on your homework, you can use this instead of, but on the exam, of course, I have to give you stuff because you can't have a computer. Now let's go to the t distribution. And what are we going to do there? Here we are on the t. Now first you have to remember your degrees of freedom is 23. Now let's put in this. This is negative 0.98. And now we want to compute a left-hand tail, same way, and compute the p-value. And there we have it, and it's 16.86%. So let's go back to our document camera, and we'll put it right here. So this right here is 16.86%. So that's this, and here, this is the one we should be using, and that's our p-value. So p is equal to 16.86%, and here p is equal to 15.39% if we want to be exact. So that's the difference in our p-values. Sorry, that's the difference in our p-values, and our conclusion's the same, but as you can see, we're a little more conservative with the t. Okay, and it might make a difference sometimes, like if you're near 5, because 5 is this magical number that people treat magically and cut it off there. Like when it's kind of like giving you an A. If you get a, I hate doing it. Grades are so clustered together, so like 89.99. Is that really different than a 90? No, but there's this cutoff that usually the data if you put it into some standard program, that's the cutoff. I never do that, by the way, and I never do this. I list 5%. I'll look at the actual value, and like with your grades, always list them in order. And if you're all clustered around one grade, I look for the biggest gap before I make that cutoff, because I just don't. I mean, certainly 90 is always going to get the A minus, but I'm not going to give 89.99. I mean, especially if like further down, there's quite a big gap. You know, that's the natural place. Otherwise, it's just not fair. Yeah?
So like for an exam or just homework questions, if n is less than 30, we're going to use the t-value.
Yeah, for this. See, we have to make these cutoffs just to, but you know, basically it's a gradual thing, but that's how we're going to do it. All right. Now, okay, let's see what's next. Okay, so you can't reject the null. The negative correlation could easily be due to chance. How about right now, let's do some iClickers. It's been so long, and let's do them in a fun way. How about, why don't you take them out? I haven't prepared any iClickers, but I think, let's look at our survey data. We have this exact question. So how about if we just go to the computer, and here's your data, and here's all the questions. There's so many of them here. I've been fascinated, and honestly, I haven't even had a chance to look at the drinking versus GPA yet, so this will be new to me too. And okay, and so why don't we just go to the scatter plots? But before we, okay, what I'm going to do is, not sex partners. I'm going to look at drinks and GPA. This is GPA and sex partners. That tells you there's not much correlation there. A little negative. But I don't know why that was up there. I must have been looking at that last time. But now we're going to look at drinks versus GPA. And let's just start it. I want you to guess if you think it's going to be negative or positive. Okay? Just guess. All right. Whether R and the slope are going to be negative or positive. So let's just start it. So negative will be negative. Oh, what's that? Negative will be A, and positive will be B. And should we do C just like so close to 0 it hardly matters? So A you think is going to be pretty negative, B is pretty positive, and C is so close to 0 it's going to not make any difference. Not be significant, really tiny. How are we going to even solve that? Not statistically significant, I guess, is 0. It's C. Or not practically significant. Which one? I didn't define that well. You can't lose on this. This is just for fun. I didn't define that question well. Like, so small it wouldn't matter to you. Let's do that instead of statistically significant. Like, so small it's like just, who cares? Even if it's statistically significant. It wouldn't stop you from drinking. It wouldn't, you don't care about it. Even if you care about your GPA. So, got it all? Everybody vote. A is negative, B is positive, and nothing for C. All right, so we'll stop it. Let's see what you did, and then we'll look at it. Okay, so most people think it's going to be significant. Well, at least a difference you'd care about. Positive, that's wishful thinking, huh? Some of you. Maybe. And this is like probably hardly matters to you. All right, let's check it out and see what happens. So what are we going to do? We're going to do drinks and GPA. And what is it? Is that right? It's positive slightly. What is it? Is that, wait a minute, there's a, oh my gosh, let's look at this. There's the regression. Oh my God, that is astounding. I got to take a look at that. I didn't see that before. Whoa. Whoa, that's about as flat as you can get. The zeros win. That is really kind of beautifully flat. All right. It never comes about that close to zero usually. Shoot. Okay, well, there it goes. I thought, what class is this? That looks like too many points for you guys. Let's see, let's get the stats on this. Oh, this isn't you. This is, who is this? 1,209 people. That must be Stat 100. Oh. You're not such a big class. Whoa, that's astounding. Let's go back. You want to see yourselves. Okay, so what did I do? Stat 100 survey 2. That's not you. You're 200. So let's choose a different one. Stat 200. All right, so why did I, 200? This is you. Okay, so now we're going to go to Scatter Plus. You want to guess again for you guys? Let's do another eye clicker. It will be fun. So you're going to do the same thing, and I'll pull up your scatter plot, and you can keep it the same or not, as you see fit. So 0 is negative. I mean, A is negative, B is positive, and C is 0, really close to 0. So you want to guess? Just guess. Fun. And then we'll see what we guessed. That was amazingly beautiful. I mean, as close to 0 as you can ever, as I've ever seen. It was like, oh. All right, let's see what you guys are. And then if you're different, we have to think about why. You might be different, or is it even statistically significant, right? Okay, so everybody, let's see what you're saying. We'll close it out and stop this. Let's see what you got. Is this bigger than it was for before? Why? Because I got so surprised. Okay, so I think you're going to be right. I think it's negative. Yeah. Okay, so let's look at this. So we're going to do, where is it? Drinks and GPA, and let's do this. Oh yeah, it's somewhat negative, but not very much. Negative 0. Okay, so what does it say? It says your GPA is 3.49. That's when you don't drink at all. Boy, is that a high GPA. Minus, this is a really tiny, drinks per week. So that's your slope. Negative 0.0068. So is that important to you for your GPA? That if you have one more drink per week, your GPA is going to fall by how many points? By 0.0068, 3 points on the average. That is not probably important, but is it statistically significant? How would we even find out? Let's do it.